the lecture today. So what happens in the last three is this problem was given, and I want to find force here in this member and in this member only in these two members. And then I'll say what's the fastest method to get these two on the part A. Forcing is right here. Force in EF and part B. Force in CD. Now, we already explained it in the last class, we talked about it, but I graded the quiz, I got some very strange answers that I didn't really expect, and we want to talk about that, because we're going to have lots of explanation questions. Maybe in the final exam they have explanation questions, multiple choices. So you need to write the answer in the correct way, in a unique way that will specify everything in a clear way. So, for example, I got an answer like use method of joints, and then there were a lot of text here. Structural analysis and blah 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 blah. It was like 3 paragraphs. But the question is, use method of joints. But what joint? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 11 joints. Each joint gives me 2 equations. 11 times 2, 22 equations. Is that the fastest way to get the force in this member? No. So what I did, unfortunately, I had to deduct some grade. Although you mentioned method of joints, but that's not the answer. You should specify. In fact, the correct answer is right here. Very short. Joint at F. Write joint equations for joint F. That's the correct answer, just 2 words. Or you could just show it like this. You could highlight it. Then that's enough to get your credit. Because I know, oh, you're talking about this joint, or this is your system. You may not even don't like this method of joint and section, this terminology. You may just say 5-step algorithm, but my system is this one, this pin. That's exactly the same. You get the force here with minimum number of equations. The second weird answer that I got is they wrote, so this is wrong. This is not unique. It doesn't uniquely specify the answer to the problem. The second wrong answer was moment around G. Well, the question is, what is your system? Well, let's say, okay, I'll write moment around G, but what is my system? If you don't exactly say what is your system, then I say, well, what if this is my system? What if this is my system? Then if you do IFED, you get 1 unknown, 2 unknown, which is actually, I'm trying to find this one, so it looks good. Known given, known, another unknown, AY, and another unknown. So can I find this force with just writing one moment around G? Let's do it. Let's start with this one. This goes through G, moment 0. Then the next one is this one, which is unknown times this distance, which we have it. So far good. And this one goes through G0, this one, 2k times this distance, 2k times this distance, 2k times this distance, so far it's good. But look, I have AX unknown showing up in the equation, AY showing up in the equation, this one is 0, and this one will show up. So how many unknowns do I have? 1, 2, 3, 4. One equation, 4 unknown. So when you say something, you should say what your system is. Now let's say you say moment on G, and then you say, this is my system. This is my system. This is my system. And now, moment on G. If you do that, then I say, you get your credit, because that's right. If this is your system, then your FPD is like, you have unknown here, and 1, 2k known here, right? That's your FPD for this system. What about moment about G? Let's start with this one. 0, this unknown times, let's say this one. Negative 2k times 1, so you get this one. That's right. So what I'm saying, when you give your answer, then you should say system shown, or you just don't write anything. You just write here system and then say moment around G0. So this is the system. That's the correct answer. But if I don't see your system, I can't give you a grade, because the answer is very confusing. Another thing which is in fact very disappointing is some student wrote, like if I want to find a force here in this member CD, I got something like, some student wrote like a system like that, and then the answer was, I do method of section with this section given, and then I can find the force in CD. Well, no, you can't. No way. This is not a correct answer. So this means the lack of understanding of how to choose system. Well, if you want to find the force inside this member, this internal force, you have to somehow cut it somewhere to isolate, to make it two systems. Otherwise, this becomes internal force and cancel out. So if you draw a 3-by diagram of this system, you get B, C, right? And then you're gonna get force like that at B, and a force like that, at D like that, and then a force like this at C. So you may get some of these unknowns, but you never get things that are inside this member, because that's internal. In fact, if you have internal force, they will cancel out, according to Newton's third law. At each single force, there is an action and reaction, action and reaction, action and reaction. They cancel out, except at the borders of the system that interact with the surrounding. You have forces that are not canceling out. Okay, so what I want to say is, whenever I give a question like that and say, explain, then you have to write something, probably as short as possible, if you can. If you cannot make it short, just explain it. But what I'm trying to say is, write something that uniquely specifies the answer. Like everything, system, how you do it, the equation, like how you do it exactly. If I have confusion that what can I do here, like what is my system, then I cannot give you full credit for that. Okay? Now let's go to the next section, which is moments of inertia. In fact, after we do moments of inertia, we're done in this course. And then we do review questions. Review quizzes and review questions. So moment of inertia, go to the next section. So, moment of inertia shown with I is defined as the surface integral we call it area moment of inertia. What I want to say is it's just an integral, it's just a formula, a mathematical construct that you see like that. And sometimes you see an integral of the first power of x. The first power is not moment of inertia. The second power is moment of inertia. The first power is used for centroid computation. As I'm going to explain right now, first we do that centroid computation, and after we know how the centroids are obtained and we get a little bit exercise, then we do the second moment of computation when we of the x to the power 2. So if you know how to do that, this should be a piece of cake. And then finally, we try to use the tables instead of doing integrals, because engineers don't want to do mathematics. But you have to do it once to understand how they drive. But once you understand how they drive, you just go to the appendix and say, well, this is the formula for moment of inertia. Now I'm going to use it. Okay? So let's first work on the first integral. How I want to show you how you get the term like this into derivation. So let's say you have an arbitrary shape. Right? It's like a potato, but it's like an arbitrary 3D object. Okay? So the shape is not like rectangle or cube or anything. So let's add some volume to it. Just put something like this. Like that. And then say this is your reference axis, xy and z. Alright. So right now what I want to do is I want to find the mass center of this, which is if the object is uniformly distributed, the density is the centroid. So in that case, you remember when we, in the first chapter, I said, if you have a triangle, the centroid is 1/3 of this base. Right here is 1/3 of B. And I said, just for a moment, right, just memorize it. Later we prove it. How we got 1/3 of B. Now I want to work on that. So now let's go to this physics. If I want to replace this object with just a single load, let's say a single load W, that the weight is equal to the weight of object at some location like x bar with respect to the center, then the moment generated by single load should be equal to the moment generated by all little tiny masses in this element, in this potato, right? As a matter of fact, if you slice it up, at this point, let's say I take a slice like that. There you go. And this part, let's say the location is x with respect to that center. This is not x bar, it's just x. Right? This little slice has a small mass, and then therefore it has a small gravity. Let's call it d weight, dw, down. So right now this is a scenario. What I want to say, I say I'm gonna add up all the moments coming from, because we're gonna have another slice here, another one here, infinite, right? If they're tiny, infinitesimal thin, I'm gonna have infinite distribution of this thing, this disks, right? And each one has a weight, and therefore they generate a moment with respect to this. So what I'm gonna say is the sum of all those moments, and that's the resultant moment, resultant MR, should be equal to moment generated by this single load. If I want to replace it with just single load, it's like balancing. You want to get rid of this and replace it with a point load, right? So what's the moment generated by this disk with respect to this point?
Weight times X.
Yeah, so it's going to be X times EW. Positive or negative? Negative. Thank you. Right? This is infinitesimal moment coming from one of these. Now, if I add them up all together, what do I get? Don't forget that this is infinitesimal. So if I add this one to the next, to the next, to the next, all from here to here, what do I get? I get sum of all these little moments from beginning the object to the end of object. Let's say the beginning of object is A, the end is B, right? So this is sum from A to B. So what happens to that sum if I have infinitesimal thickness? If this thickness is very, very small, infinitesimal, what happens? What should I do with that sign? With a summation notation here. What happens to this summation? It becomes integral. So in fact, this becomes integral negative x dw from A to B. So that's the resultant moment, right? That's the resultant moment of all these little disks everywhere with respect to this. Now, answer your question. What's the moment of this single load acting at x bar with respect to x? It's just only one. It doesn't need a sum, right? So that is equal to distance x bar times the weight. Positive or negative? Negative. So this is, let's say, 2, equation 2, and this is equation 1. Equation 1. Now the law of equilibrium says those should be equal. In fact, they should be balanced in order to be able to say they are equivalent. So I can get rid of that potato and just have one single load, right? So in fact, this should be equal, which is integral A to B, negative x e w. This should be equal to this one, which is negative x bar w. Then this gives me equation for x bar, the location that the point load acts, which is, if the object is uniformly distributed, is centroid. Okay, so solve for x bar. You get x bar is equal to integral x dw A to B over the weight. That's it. That's a formula, in fact, that tells you where is that centroid, the location of centroid. So if you can evaluate this integral, this is a calculus 2 problem. Calculus 2. If you can evaluate the integral over the object, then you get a centroid. So let's talk about the weight. The weight, we agree that the weight of this object is sum of all these infinitesimal weights, dw's. And if you go to the limit, this becomes integral dw. So instead of weight, I can put integral dw. So in fact, the formula is x dw over integral dW from A to B. A to B. That's the formula for center of gravity, or center of mass. Now let's say the object is uniformly distributed. Density is mass over volume equal to dm over dv. Then dm is equal to rho dv. For this is the slice. The density of this slice on its volume is its mass. And d omega, here you can simplify that. dw, this d wave is mass, so you can, instead of dw, you can put mass dm on g, right? Body force is equal to mass times g. Instead of dm, you can put rho dv times g, right? So here you get integral x rho dvg from A to B over integral rho dvg from A to B. Okay, so you can see g cancel out with g, rho cancel out with rho if uniformly distributed. So this center x bar, which is center of mass, become center of volume x dv from A to B. Integral dv from A to B. Now, if your object is also has uniform thickness, so let's say this is not potato, it has uniform thickness. So we can say dv is equal to a length time dA, which is this is the depth. So you can say this is equal to integral x dA from A to B over integral dA A to B. As you can see, the formula finally becomes x bar integral x dA over integral dA. This is what we produce actually. So back to the main question, you see we get a formula that is x multiplied by dA. You get things like that. That comes from this calculation, laws of equilibrium. In dynamics, you get things like mass moment of inertia. You get some mass here. Later on, in the second part of this class, mechanics of material, there's a vector state. Second part, mechanics of material. You, through some laws of beam, when you do beam analysis, so this is a cross-section beam, and this beam is under some load, so it starts bending and has some weird shape. Then in the derivation of that, we get integral, like second order integral. So right now we want to have a method to compute that. As an engineer, you should be able to compute these guys without using integrals. You should be able to compute it immediately, very quickly, using tables. But before we reach that point, I want to explain the basics. So we want to do this integral just one time, just to understand, this formula is going from doing this. Once you understand it, you'll never do integral. Use the formula in the table. So let me give you an example. Let's go to one of these classical examples here. Let's say folder, and instruction, right? 1 meter. 6 meter and 3 meters. And the material type density is 10,000 kilogram per meter square. So in fact, I have a concrete slab or some dense material that is, it has a wedge-shaped type. Is mounted at pin, this pin location here pinned to the ground, and here you have a roller so you can slide, right? The density of this object is given, and then the question is, find the reaction at pin. This pin is the pin, right? Inside. Find the reaction in this pin. So who can solve this problem? Let's give you opportunity for midterm waiver.
What is the question?
Question is find, let's say this is point A, B. Find the force in pin A, right here. So this huge structure slab is mounted on pin A, roller here. Find the force in pin A. That's the question. Now, although this is a little bit off the topic of the centroid, but you need to use this centroid computation at some point to find the centroids. Can you do that? Well, you remember before the midterm, first chapter, I said, if you have a triangle, where is the centroid? 1/3. If this is B and H, the centroid is going to be 1/3 of B and 1/3 of H. So it's 1/3 of whatever this is, base and height.
Do we need to know, are we trying to figure out, or are we going to need to figure out where A is in terms of?
No, this is the base and this is the height. There you go, base and height.
So where is A in terms of the base and height?
Well, let's say this is a very corner. At the very, very, very corner, yeah. Let's assume that this is very, very corner, right here. Let's say this is right here. So how do you solve this problem? What was the 5 steps to solve any problem? System, free body diagram, equation, solve, verify. So if you go through that 5 steps, you can find the force in all the pins. In fact, let's do that. Let's say this is as your system, right? Let's say draw some border line. So this is my system. Now the next thing is FPD, free body diagram. Well, if you draw FPD, what you have here, this is a pin, right? You're gonna have AY and AX, right? Then you continue walking here, then you have BY, and then you come back to the original point. Now you go to body force. Is surface force. Do I have body force?
Yes.
Yes. So how much is the body force? mg, right? Body force is mg. W. And what is m? Well, the really neat contribution is just,
Volume over density.
huh?
Volume over density.
Yeah. So, mass is, density is mass over volume. So mass is equal to density times volume instead of mass. And then you have G. So let's compute weight. What's the density? 10 to 3, right? Times volume. Volume of this guy is the base area, which is 3 times 6, 18 divided by 2, 9 times height. So 9 times 1. This is volume. This is density. So that's going to give you, this is, so this is going to give you rho v, right? And then finally multiplied by 9.81 G. See that? So whatever this gives you, this is your mass. Okay? Now the question is, where should I put it? On the free body diagram. Yeah.
At 1 meter in the y and 2 meters in the x.
Yes. So in fact, that's correct. From here, 2 meter, which is because this is 1/3 of base. So base is 6, 1/3 of 6 is 2 meter. And 1 meter here, 1/3 of 3. So it's a point here. You put it right here. Weight. See that? So now if you, this is your FVD. Now if you go to the equations, the step 3 equations, then you know that a lot of equations can be avoided by just directly writing moment around B with respect to this axis. Let's call this Z. So what I get, summation of moment around B is equal to 0. So that will give me, let's start with By. By is going to be no moment. The next thing is W. W times this distance, which is 4, thank you. Positive or negative? Yeah. Right? And then the next thing is AY times say AY times, assuming that this is at the very corner. 6. Thank you. Is equal to 0. So in fact, AY, the answer to the problem is 4/6 times W, or 1/3, 2/3 of the weight. So the whatever the weight comes from here, this is almost 10, right? 10 times, this is 10 to 4.
It's 882,000.
Yeah, this is 4, but 5, 10, almost 1 meg, 1 meganewton, 1 meganewton. You see, 10, 10, 10, 10, 10 to 6, 1, 2, and 3, and 3. See, almost 1 meganewton, almost close. It's like 800 something, or almost. So 1/3 of 2/3 of 1 meganewton, 2/3 of meganewton. So it's a significant force. But look, you didn't say, how did you prove that this weight goes through 1/3 of base and 1/3 of height? In fact, you can rephrase the question as, how did you end up with, in the first chapter, you said just memorize it, 1/3 of the base. Now I say, well, here is the answer. We want to prove it. Now you see the application that this really works. This has application, again, design a structure, right? So how can you prove it? Well, using this formula. Let's say you have a triangle with base B and height H, right? Then the question is prove, let's write it here, prove that x bar is equal to b over 3. Or the centroid is 1/3 of the base. Prove it. Well, I already give this first order integral.
What is B?
B is the base. Here, let's say in that example B is 6. But here we just keep it B, like a parameter, arbitrary. Now I give this as a vector variable. In fact, this is not the vector statics problem. This is calculus 2 problem.
What was the question?
Prove that the x bar is 1/3 of base. Or the centroid, this is centroid. The centroid is 1/3 of the base. Prove it. Use this formula and prove it. That means just evaluate that integral. Go to calculus 2 and evaluate that integral over this integral. You see that? That's the thing we did in calculus. Give you some suggestions. Let's say your reference system, put it right here, XY, at the corner, XY. This is your coordinate system. And now this is your domain from 0 to B, from 0 to A.
What are we solving for?
This integral.
And we're just trying to prove
Start with this integral, so you do integral x dA. What is your dA? Over this area.
And we're just trying to prove that.
And then we want to end up, starting with this side, we end up with x bar is equal to b over 3. That means the centroid is at 1/3 of the base. Mathematical, solid, rigid mathematical proof. And this comes, you may ask, how did I get this? Well, we just got it using equilibrium. I replaced the moment of all the slices with just single moment. So it's a solid proof of why the centroid is at 1/3 of the base in triangle. Yeah. You want to do it?
Yeah.
All right. Yeah, you guys already got a full 100%, right? In the midterm, and then it's like an overkill. Usually, the thing that happens in thanks for coming. The thing that happens in UTC is some students are like over prepared. In other words, like I can't explain it. It's just they're very good. And unfortunately, some students are absolutely not prepared. And we usually don't have average students. I don't know why. So when we do that Gaussian distribution, the bell curve, it never happens. They're either very good or very bad. So well, look, before you react. This, how did you get B over 3?
I thought you gave
No, this, you have to.
You gotta prove that, ACC.
You only have this side, you don't have this side. So here, in fact, this is X bar, this is not B over 3. So now you go ahead, and the next thing, you can't take this X out of the integral. See that, if we do like integral X dx, you can't take this X out, because that's a variable of integration. Oh, okay, all right. Well, a quick review of calculus may help. So in fact, this guy, let's start with what heroes, and instead of A, DA. So what's DA here? Well, take the element like that. That's your DA. And this has the base. So if this location is X, I'm doing exactly what I did here. I have a slice, location X, some people call it element. I have an element of the slice, a location X. And the base, you want to do it?
Can I try? I mean.
Yeah, sure. The base is dx, right? And the height, let's say yx, we don't know. It's a function of x. It will shrink when you move the x. Now, yeah, well, no, unfortunately you can't. Let's go step by step. Let's go step by step. Let's do dA. First, write it. What's the area of this slice?
Are you integrating with respect to A?
No, I'm integrating with respect to this point over x from 0 to b. In fact, I'm adding all this infinitesimal tiny slices together in this integral. So, in order to evaluate this integral, you remember, you had to find the formula for dA. Plug it in, and then convert this integral into a one
So the only thing you
dimensional, one variable integral, and then take the integration.
yeah.
So, what's, if this bar,
Unless he
look at
just
this
substituted
bar.
X or something.
If this bar approximated the rectangle like this, so the area of this bar is what?
B times H.
No, this is
Oh, dx times.
yeah. So write dA, the area.
What is X? Because like when you say integrate with respect to X, dA is in essence dy dx. So if we're integrating with respect to X, then what he was starting to do makes perfectly good sense to me because you're integrating X, unless X is something else.
You're integrating over dA. So if you have to find an expression for dA. So we'll reach to that point. Just wait.
Okay.
You're integrating over dA. You're not integrating over x or y. You're integrating over dA. So dA, before we actually do this, let's write it here. Let's write dA is equal to the area of this bar. What's the area of this bar? The base dx times the height y of x. That's it. Right? So again, let's finish up this. We don't have y of x. So what is y of x? Can you find? You have to find y of x in terms of x. So you put it there and take the integral. Everything should be in terms of x finally. No, the y of x is the equation of a line goes through these 2 points. You see? You see that? It's a line. Y of x is a line
So this.
going from, yeah, you're getting close to that, but it's not that. A line starting from 0 and h, this point, and then goes through b and 0. You see? 0 and h goes through b and 0. So what's the equation of line between 2 points?
Y minus.
Uh-huh.
Negative h over b.
No, that's not it. If x is 0, what do you get?
So that negative h over b.
Yeah, but you should get only h. You see that? So if you write the equation the way you said, there is a formula that you, if you read it, you need to see the formula for equation of line given 2 points, beginning and end. Or not beginning and end, the line that passed through two points. Then you get the equation for that. Y minus y1 is equal to y2 over y1, y2 minus y1 over x2 minus x1, times x minus x1. That formula. And if you do that, then you get, yeah, he's getting it. Yeah, in fact, it's going to be like that. You're getting close to that. It's going to be yx is going to be h times 1 minus x over b. Right? Now plug if x is 0, then what do you get?
H times 1, H.
Which is h. You see, if x 0, the y is h. If x is b, what do you get?
0.
Yeah, here. So that's exactly the line passing through that. Now, plug that into, so this is your yx, plug it into dA, and then plug it here. So there you go, let's move back for it. So start, writing integral. So first of all, where are a and b? If you're integrating, mathematically everything is x. It's from 0 to b. So that's going to be from 0 to b. X times dA is, yeah, dA is, yeah. Right. Now this is just a matter of a simple integral. Now, I'll give you optional homework. You don't need to tell me. Okay? Go home and evaluate that integral. The end result should be top divided by bottom should simplify to b over 3. And then you say, aha, now the centroid is 1/3 of the base. The formula that you memorized it in the first chapter. Now you have a solid mathematical proof for that.
Do you want me to keep going?
If you want to, but I think we're out of time now. But thank you.